Welcome, welcome. Grab your cup of tea. I've got mine. Get cozy and get ready for some math. A new math, actually. So, my friend and I think we're making a new math. Maybe we're wrong, maybe we're right. But what we are definitely doing, even if it happens that we're not making a new math, is we're playing around with math by ourselves. And we're making things up. And it's really fun. So I'm going to explain this world of math to you while it's fresh on my mind right now. And maybe we'll backtrack a little bit. So, here is how this world is defined. We have shapes. We have a face position and a line position. So, let me draw this kind of like a graph. So let's say we have a square. There's one person sitting at face position that's looking at the face of the shape. So they will see this. So face position, you will see this. Then there's another person sitting at line position, and they see just a line. They see this projection length. So that is line position. Okay? So we've defined that we have two different positions. The line position, essentially, is a length, which is y2 minus y1. At any given point, on this x-axis, we don't care which point, as long as it's at one point. So like this is a line. This is not a shape. This is just a line that we see. So here we're working in 2 dimensions in face position, and in line position we're working in 1 dimension. Now, what we're going to say is that every single shape has a value at a line position. So for now, let me just call this line position value, okay? Line position value. Every shape has one, and it's equal to the length of the visible line. Line position value, okay. Every shape has an LPV, which is equal to y2 minus y1. Cool. And we can say that this shape, or that this value, this value is dependent on the size of the shape and its degree of rotation, right? So let's take this square, for example. If I have this square, its line position value is like right here, if it's facing this way. Versus if I turn the shape like this, the line position value becomes this diagonal line. So like when I turn it to line position value, what you will see is just from this diagonal to this point. You're not going to see any of these things, you're just going to see the line. So we're going to make a little bit of a notation for this. We're going to say, we're going to call like shapes different letters. So let's just call a circle like C, and let's just call a square S for now. And we're going to kind of write this as a function. So the way we're going to denote it is we're going to put like LPV, the line position value of circle 1, and then we're going to specify a degree, so degree 0, is going to be equal to this length. Let's just pretend the length is 1 at the moment. This square has a side length of 1, and this circle has a diameter of 1. So this square, we're going to say LPV of square 1 at degree 0 is equal to 1. Okay? And so every time we say degree 0, we mean for a shape to have its flat end, like its flat side, facing up. So like horizontal to the x-axis. So this would be degree 0 for a square. This would not be degree 0. So like this would be 45 degrees. So if we say that the LPV of the square, same square, at 45 degrees would be equal to what? We have the diagonal of a square. Whenever we draw a square, it looks a little rectangular, but let's pretend it's a square, right? We have x and we have x. And we have the Pythagorean theorem that we can use because we have two triangles and we have a right angle, right? So in regular Pythagorean theorem, we have a, b, and c, and we have that a squared plus b squared equals c squared, right? So in order to find what c is, we're going to do the square root of a squared plus b squared equals c. Cool? But now let's take a look at this square where a and b are equal. A and b are just x. So x squared plus x squared is equal to the square root of 2x squared equals c. And so we can take out the x squared. We can make it x square root of 2 equals c, which is right over here. And so our x at this moment is 1 because 1 is the side length that I've chosen for this square. So over here, our line position value would be square root of 2. But we can substitute any side length into here. Cool. So this is how we're just going to denote things, okay? Now the way we're going to compare different shapes, or the way we're going to define something as the same, is by using the line position value. So this is super important, okay? So that's what this paper kind of explains. We have a line position, a face position, we have shapes, and let's just be clear on how we define shapes, which is not a line. A line only has one dimension and shapes have two dimensions. So we have a line position, a face position, a shape, and then we have a line position value. And we're going to define shapes as equal if their line position value is equal. So for example, in this scenario over here, we have these two shapes as equal because their line position value is equal. 1 is equal to 1. So using this example above, circle 1 of degree 0 is equal to square 1 of degree 0. And in this case, we just have the diameter of the circle to be 1 and the side length of the square to be 1. Cool. So because the line position values are equal. Now, here is a rule about how we define transformations in this world of math. We say that the so-called person sitting at face position is allowed to change the shape. So if I'm sitting at face position and I have this circle with a diameter of 1, I'm allowed to change it to a square which has a line position value of 1. Now, if this square has a side length of 1, it needs to be at degree 0, right? So what we're looking for specifically is the line position value. So person at face position can change the shape under the condition that the new shape has the same line position value. Line position value. Now the person at the line position is allowed to rotate the shape. Is allowed to rotate the shape. The shape, well, by any degree. So this square, well, let's start with the circle, right? At line position, you can rotate the circle like this. For the circle, the line position value would not change if you rotate it, right? And for the square, it would. It changes as you rotate it. And so changing the shape, you don't really change the shape because you keep the same line position value, and that's why you're allowed to do that. So it's not totally a transformation. It's kind of like an identity transformation, but it's allowed to happen. You are changing the shape, technically. Now, the person at line position, they can rotate the shape. Here is where sometimes the line position value will stay the same and sometimes it will change. And yeah, there's no guarantee. Exactly. So like the person at line position, unless they're rotating a circle, it's essentially, or they're rotating, okay, let me not get too ahead of myself. We have a person at line position, they're allowed to rotate the shape. That's what we're saying, by any degree. By any degree. Okay, so given these two possible changes that we're allowed to make, here's what can happen. You can have this circle, and we can say that the person at face position does one move and changes the circle to a square at 0 degrees. Okay, so then we have the person at line position. Let's say they change this square and they rotate it to 45 degrees so that the line position value now becomes the diagonal, which is like square root of 2. Now, the person at face position can change this square into a bigger square, where this square at 0 degrees of rotation has the same line position value as this square at 45 degrees of rotation. So it can be changed. And so the transformation can happen from this circle into this bigger line position value with like 3 moves, right? So this switch to this is 1 move, rotated is a 2nd move, switch to the bigger shape is the 3rd move. Well, yeah, I guess to a bigger area is the 3rd move because the line position value is the same within the 2nd move and the 3rd move. So within 2 moves, you can increase the line position value. Within 3 moves, you can increase the area of the shape. This could be a circle if we wanted as well, that just has a bigger diameter. And yeah, so we are starting with just basic things at the moment. We're not going to expand it too far into like other shapes yet, because this is new. And we always start with the simplest thing that we can possibly do. right? So for example, like with the square, let's not think about like all infinite rotations. Let's just think about, okay, 0 degrees, 45 degrees, 90 degrees, so on. Cool. So, here's some experiment that I tried given all of these rules. I said, hold on. Yep, that's kind of what I just talked about. So, one interesting thing that we can notice before I go into this experiment is that the line position value of a circle always remains the same no matter how much you rotate it, right? So here, we have a rule, we have something consistent in our world of mathematics, in this world of mathematics. No matter how much you rotate the circle, its line position value will always be the diameter. Cool? Cool. So, we have the line position value of circle A, and let's say we did these 3 moves using a square to get a bigger circle. So like let's say that after we changed this circle into a square and we rotated the circle, let's pretend the third shape we got was a circle with this diameter. So the conclusion is that you can always change a circle of line position value A, of diameter A, into a circle with the line position value of A times the square root of 2, right? So that takes like 3 moves over here. And then you can change that with another 3 moves into a circle that has a diameter of 2 times A, which is 2 times the original circle. So these are just things that we can do. And we're trying to figure out what more we can do or what less we can do. And there's like all sorts of questions. So like when you're creating something new, first you're trying to see what can you do with these, I guess, shapes, objects, rules that you've created. Like what can you do from here? But then also, what questions can you ask, right? So given this first part that I've just explained, here's somewhat of what I've come up with. Like, is this shape equal to this shape is a question that you can ask. And the answer would be, if the line position values are equal, then yes. Or can this shape be transformed into blank shape? I don't know currently the universal answer to that question, but it's a question you can ask. Like, can a circle be transformed into another circle that's twice the radius? The answer is yes, because we just looked at that particular example. Can a circle be transformed into a square? Yes, if the line position value is the same. So yes, if the diameter of the circle is equal to the side length of the square. Can a circle be transformed into a bigger square? Also yes. If, depending on the scale, right, it would be just a factor times the square root of 2. And so you would just be using multiple rotations of squares and just bigger squares in order to continue getting into, a bigger square or bigger circle. So we have some examples that we can answer this question for, but we don't have others yet, which we can come up with them. Here's the third question. So like if yes, right, like if you can transform blank shape into blank shape, then what is the minimum number of steps needed to do that, right? Because you could keep transforming this circle into this square over and over and over a million times, right? And into this square, back into this square, back into this square, whatever. So you can take the infinite number of steps to get to this same place. So the question that is, I guess, more meaningful to ask is the minimum number of steps, right? And so here we have 3. This changes into this. Rotating, we're counting the rotating as a movement because you're changing the LPV value. LPV value, so you're actually changing the shape here. So the square at 0 degrees is not the same shape as the square at 45 degrees is what we're calling it. So that would be move number 2, and then we switch it to this square, which is move number 3. So a minimum to change a circle into a square that has a side length of like a factor times the square root of 2 is a minimum of 3 moves, depending on what the original diameter was. That's what the factor would be. So that's something we can ask. The question then, can I say that you can always transform a circle from LPVA into a circle of LPVA times the square root of 2 in 3 moves, right? Can I always do that? I think the answer is yes. So here we have like one property already of something that exists. Maybe even 2, because we figured out the property, that when you rotate the circle, the LPV value remains the same. I guess that's kind of like a characteristic. So that's kind of like a characteristic. What's the difference between a characteristic and a property? I could Google it. I'm not going to right now because I don't think that's the most important thing at this particular moment. The point is, we're figuring things out and we're, finding more information. So, there's other, questions. Every odd, every even transformation. But here's something new that we are actually going to consider right now. So, remember how I was talking about, do I have more paper? Yeah, okay, good. So remember how I was talking about how rotating the shape changes its line position value, right? So here's the newest thing that I was thinking about today. So first I was like, okay, let me just draw this out. This is the transformation that we just kind of looked at. Circle goes to square, goes to rotated circle, whatever. So then I was like, okay, since the LPV is the same for these shapes, we're calling them equal. Since the LPV is the same for these shapes, we're calling them equal. So then I'm like, okay, so what does that really mean? What is the more general idea of what makes a shape equal to another, right? And then I was like, well, think about it. We have this diameter, we have this side length, we have this side length. But then we can expand it down. As long as this LPV value remains the same, the shapes are the same. So we can draw this LPV, right? And we can make these lines over here at the top and the bottom of this, line position view. And anything that we draw inside, as long as one part of the shape touches somewhere on the top line and another part of the shape touches somewhere on the bottom line, all of these shapes are equal to each other. You can make this rectangle as long as you want. You can make this shape however you want to make it. These shapes are going to be equal to each other because they have the same line position value. And then I was thinking about the rotation of the shape, right? So when we rotate the shape, it's going to have a different line position value, and we're defining that as a different shape. However, at face position, the shape is the shape, right? So the circle is going to be the circle, the square is going to be the square, albeit rotated. So then I was like, well, let's think about pairs, because there's going to be a minimum line position value for each shape, and there's going to be a maximum line position value for each shape. So let's think about this. The one for the circle is the same. The minimum and the maximum is the same that you can translate to. For a square, the minimum is the side length, but the maximum is square root of 2 times that side length, right? And so what if we try some other shapes like a triangle, a rectangle? So like what happens? So let me just get maybe this paper. So essentially with these pairs, so like, yeah, so for a circle, let's say we're gonna make, let's just call this the diameter, right? So like the lowest line position value is going to be the diameter and the highest is going to be the diameter. So here we have this pair, which is the diameter and the diameter. And then we have the square. We're going to make this, an X and over here. So then the shortest line position value is an X and the longest line position value is X times the square root of 2. Right? But then everything gets more complicated once we move on to a triangle and a rectangle and other shapes. So, one thing at a time. Since we have this pair, the question then becomes, why don't we just use it as a ratio, right? So like the diameter over the diameter, the ratio for a circle is going to be 1 between the max and the min LPV value. And so I made this question, which is, could it be a rule in this mathematical universe that if the max LPV is equal to the min LPV, then can you conclude that the shape is a circle? Like if you don't know anything but the max and the min, like this, then can you conclude that the shape is a circle? Even better than that, if you just know the ratio, which is 1, are you always, if you always know that, if you know the ratio between the min and the max LPV, can you always determine what shape it is the big general question. At first I was thinking maybe not, I don't know. For a circle you can, because no other shape is going to have, a ratio of 1 between the max and the min LPV value. Because no matter how you turn this, it's always going to be just the circle. I think. We tried some counterexamples. We tried a flower shape, that if you turn a flower shape, wouldn't you also still have the same LPV no matter how you turned it? And it was the conclusion was no, because there's going to be the time when the petals are at their points, and then there's going to be the times where it's in between type thing. So we concluded the answer is probably at the moment that if the ratio between max and min LPV is 1, the shape we have is a circle. Yep. Now, we also concluded that let's do the min over the max LPV. So this is X over X squared root of 2. We take out the X's. So the ratio between min and max LPV for a square is 1 over square root of 2. So if we have 1 over square root of 2, it's a square. Now, let's get into triangles. What is the min and the max LPV of a triangle? So for a right triangle, this is kind of simple, right? So we have this right triangle, square root of 2, 1, and 1. So the largest side is going to be the hypotenuse of the triangle. And the shortest one is going to be this like right angle bisector, which is also the altitude. And we can calculate that as, what was the answer for that? It was like square root of 1/2 goes right over here, right? But then the interesting thing becomes is that we want to generalize it to all triangles. So like we can use the Pythagorean theorem just on a right triangle. We can use SOHCAHTOA just on a right triangle, but we can't use those things. We can't use those things in another triangles, right? Like we have isosceles triangles, we have equilateral triangles, where like x equals x, or like x like this, right? So we get to this idea that we have to use the altitude. The altitude will always be the shortest line in a, well, no. Hold on. The ratio between the max and the min. So we decided that the maximum, we decided that the maximum is going to be the base, so we're just going to call the base of a triangle the maximum, okay? Equals the maximum LPV. And it like, which is whatever the longest side is. And then we know the formula for area. It equals to 1/2 base times height. And height is this altitude length that we're looking for, which is the smallest length. So we just reorder this formula. So we get that the area of the triangle times 2 divided by the base is equal to the height, which is equal to the min line position value. So the pair that we get over here is 2 times the area divided by the base, comma, the base. Now if we think of that ratio, so that means we do 2 times the area divided by the base times 1 over the base, so like we put the ratio where this becomes the denominator, and so we get essentially 2a over b squared. So a and b can be different values, but that theoretically this works for every single triangle. So, I accidentally crossed that out. Okay, well, so we have now this new ratio, but this one is actually dependent on the lengths that we have in the triangle and the area as well. Right? So like for the circle and the square, we have numbers. No matter what circle you have, no matter what square you have, the ratio, no matter like what scale you scale it to, is always going to be 1 for a circle and 1 over squared, 2 for a square. Triangle, we have a range, right? But we know that, even though there's a range, it follows a specific formula, which is this. Now, we also have a rectangle, right? So a square is a rectangle, but then what about a rectangle that's not a square? The rectangle. So when we have a rectangle, we have the length, which is the longest side, and the width, which is the shortest side of the rectangle. So here we can easily determine that the width is going to be the shortest, line position value, and then this diagonal is going to be the longest line position value, which is essentially, once again, that Pythagorean theorem formula where we have a squared plus b squared equals c squared. So L squared plus W squared equals this diagonal squared. So we move the square root and we have the square root of L squared plus W squared. And so we have our pair, and then we also have our ratio, that the ratio for the rectangle is going to be the width divided by the square root of the length squared plus the width squared. That's our ratio over here. Now, here is where it gets more complicated. A hexagon. So, what do you do with a hexagon? Number one, it's hard to draw a hexagon. Number two, it's harder to draw an octagon than it is to draw a hexagon. But so, here we are. Actually, let me go back for 1 second. We have this triangle over here, and notice how it's based on the area, right? Which is divided by the base squared. How do you find the area if you don't have the height? Right? Like the reason we were using this is because we wanted to calculate the height because we don't have it. We're looking for the height, right? Because that's what our that's what our minimum line position value is. It's the height, it's the altitude of the triangle. That's what we need to calculate. And we can calculate it by rearranging this formula, area equals 1/2 base times height, which is great, which is absolutely great. However, how does one get area in another way without having the height? How else do you find the area of a triangle? We have no idea. And so that's where we're kind of confused at the moment. Like, this is correct. This ratio is correct. It is 2 times the area of the triangle divided by the base squared. The ratio is perfectly practical. But could you ever actually calculate it if you don't have the height? Like, could you ever actually calculate the minimum, line position value if you don't have the height? The height. Because, in a right triangle, right, like we talked about it, we can use the Pythagorean theorem, but we can't for the other ones. That's the point. So how in the other ones would you do that? Anyway, so this is a problematic thing that we have realized, that we don't know how that would happen. The math is fine, but how else do you find the area? We don't know. So when we got to the hexagon, we were trying at first not to use this area of the triangle, right? We were looking at different ways to split it up. It's like, okay, in a hexagon, you have equilateral triangles. Or we can split up a hexagon like this, right? We can make a big rectangle, and then we're going to have these 2 triangles. That's going to be like this isosceles triangle. Or, we do have some right angles, which is cool because we want the right angles because we want to be able to use something like Pythagorean theorem, maybe. The thing is that all of this information that we're trying to look for, which is like the maximum line position value and the minimum line position value, it's entirely based on the information of the length of one side of the shape, essentially. In the circle, we have the diameter. In the square, we have I guess that we would just have to define the area, maybe. We get to choose, right? We're creating, we're exploring it, discovering it, so we get to choose how we define it, but this almost looks like a football field. American football. Anyway, so we have a hexagon. And the way we ended up figuring this out, or I kind of suggested, like, let's forget about the problematic thing of not knowing the area without the height, and let's just use it, because here we have triangles, and they're equilateral triangles. We got triangles, and so from this line to this line, that is going to be our minimum line position value, because it's the same thing as this, which is the flat side to the flat side. And so it's just going to be 2 times the altitude. And we have the altitude right here, which is 2 times the area over the base. So it's like, okay, so the minimum is going to be 2 times the area of the triangle divided by the base of the triangle, which we are going to call x because it's an equilateral triangle, so all of these are the same. So divided by x, the base. Okay, fine. So then what's the max? The max is this line right here, which is 2 times the base, just x plus x, so we got 2x. So that's our pair, of the min and the max line position value for the hexagon. But now take a look at this, right? When we multiply this together, so when we find our ratio, we put min over max. We do 2 times 2 times the area of the triangle divided by x times 1 over 2x. We can cross out this 2. We get x squared, so we get 2 times the area of the triangle divided by x squared. Now, would you look at this ratio? 2 times the area of the triangle divided by x squared is equal to 2 times the area of the triangle divided by, here we called it b squared, base squared, but x and b are essentially the same. So the answer to my first question, which was, if you have the ratio, if you have the line position value ratio of like the min to the max, can you know what shape you have? And the answer is no. The answer is no, because here we just found an example where the ratio is the same whether you have a triangle or a hexagon. Crazy. Like crazy. So that answer is no. But then it becomes even more curious, like, is there a way to generalize this even more? How, can I figure out how many sides a shape has to have? Like, let's say, like, equal length sides. Like, let's look at the regular polygons, like pentagons, and, the 7-sided polygons. We're just going to leave that for a little bit later because we're going to just continue with the easier shapes for now. So the question though becomes like, oh, well, what I notice, right, is that we had equilateral triangles here in the hexagon. So if there's another shape that has more sides but still has equilateral triangles, I think that we're going to have the same exact ratio. Though the other question I have on my mind is that since this has equilateral triangles and we got this ratio, does that mean we accidentally got this ratio just for equilateral triangles and not for all triangles in general? We don't know. We don't know yet. But we have yet to figure it out. But the thing is, right, it's like another characteristic of shapes, which is this like ratio of min to max line position value. It's like a characteristic. It's not like we made up the definitions, right, of the face value, of the line position value. We defined the line position value, and then we like looked for it for the different shapes. And these things, these ratios, like the min and the max, we defined like those original concepts, but we didn't define the ratios. Those appeared out of the definitions that we created and the rules that we gave. And so these are like inherent characteristics to these shapes, which is wild. It's like, that's just wild. And so partially what I was doing right now is like kind of explaining this, but let's now try the next step of, that's as far as we got so far. So let me try to do the next one, and we'll just go through this process of continuing. Well, how do we do this? Like, how do we do this? So when we have an octagon, what do? Because an octagon, it has isosceles triangles. And, we could still use how do you draw an octagon? So I have 1, 2, 3, 4, 5, 6, 7, 8. It's not the best octagon. I do recognize that using like a computer at this point, something like GeoGebra at the minimum would be helpful. But maybe I'll try it later and see how that goes. That's probably going to end up being the answer. Because like we have this octagon, right? And we know that all of these triangles are isosceles. But then what happens is that when we're looking to find what the minimum and maximum line position value is, the maximum is going to be this. Ooh, maybe we can make some sort of like circle and find the diameter of the circle, and that would be the maximum. Or like radius. Hey. Okay, so we got this no. Damn. Okay, hold on. I got really excited for a second because I was like, look, if this was still equilateral, like then we could say that this side was x and this side was x, and then we'd have this radius, which is x, and we'd find the circle. Or, I mean, if we had the radius, we'd just double it. We don't need the circle at all. I don't know why I'm talking about circles. But we have this x, which is the side length. We need this side length, essentially, because the maximum line position value is going to be 2 times this side length of this triangle, which is isosceles, so that we know that this angle is equal to this angle, and we essentially know that this angle is 45 degrees because, an entire circle has 360 degrees, and we have 8 sections, so this is a 45 degree angle, which makes each of these 67.5 degree angles. And let's see. So this would be the maximum that we're looking for, and then the minimum would be between between 2 of the flat sides. So it would be like this altitude plus this altitude. So it would be the altitude of these triangles, while the max would be the side lengths, 2 times the side lengths of these triangles. So how do we, if we have x, well, right, we can do like, and here comes the problem of I don't remember how to do trigonometry, and why I really need to learn it is even just like to continue on this math world that we're starting to do. So, and my friend, like, he's doing some really cool animations for this in, what are we using there? Desmos? Yeah, in Desmos. But the thing is, in order to make the animations in Desmos, you kind of need, like, you kind of need some equations and formulas and numbers to figure out, you know, what to do, how to make those animations. So, oh, and there's another really cool thing I made in Desmos, but I can't show it to you right now. Maybe I'll make a video specifically just on that real quick, just link it to here later. It has to do with the transformation of a circle into a square into a bigger LPV value. And it's sort of like that equation of like the increase. So we originally, like, we know that the ratio for the square, right, is that every time we increase by radical 2. But like when we increase this original diameter to this square, we are now increasing this diameter into this bigger diameter. So like the original value is higher. So we're not just doing, you know, 1 times radical 2, 2 times radical 2, 3 times radical 2. It's like, no, we're doing a times radical 2, and a becomes like bigger, and so then a times radical 2 times radical 2, right? And then you put the brackets around and times radical 2. And it was completely stumping me because like I had, you know, graphed the function of like, you know, y equals x radical 2, and it didn't work at all. We ended up having to do like we ended up having to make x like an exponent. And I don't remember whether it was it like 1? No. Was it like radical 2 to the x? Anyway, something like that. Point being, I actually should have that written somewhere over here. I was like, how do you do this? And then here it was. It was a times a, which was like the factor, like the original starting point, times the square root of 2 to the power of x. Yeah, because I was like, it works. My equation works. No, it doesn't. It's like, how do I find the function? This is the function. What it means, I don't know. It's like, it's kind of like where you plugging, I don't know, this. Anyway. I don't know how to do this. So, now keep in mind, I don't think I'm going to keep talking. I think I'm just going to go take a break. However, the questions that we have are, look for the more general form of the Pythagorean theorem, because I'm pretty sure there is one. I was told there is one that applies not just to, you know, right triangles, but also to any triangle. So maybe I can apply that over here. And then also the next question that is unsolved is there a way to get the altitude of a triangle without using area? You know, is there a way to calculate the height of a triangle without using its area? Those are the two big questions that we have. And everything that I just explained was at once me sitting here being like, well, what happens if I do this? And what happens if I do this? And does this work? Yes. Does this work? No. Does this work? Yes. Hey, look, maybe they each have, you know, their own characteristic of this, or maybe they have their own ratio. Maybe not. And it's like, it is really an act of exploration. That's what math is. You're looking for the patterns, and you find one specific case, and then you start generalizing it. Like I could use specific values for a triangle, or now I can change it to say x. Ooh, what if I can just hold up? You know what? Here's what we're going to do right now. We're just going to define this value as like let's just define it as r, because technically it would be the same thing as a radius of a circle. So let's just define this as r, okay? And in that case, if we have the r, then the ratio for the octagon would be, so let's see, that the max, this is the max, right? So it's going to be 2 times r, 2 r. The max is 2r. So then what is the minimum? The minimum is the side length, which is, once again, we're at the altitude. And so here we have this altitude, and we do have this right triangle in which the r becomes the hypotenuse because it's the thing opposite the right triangle. So we have x plus x squared plus the height squared equals this r squared. So then we would do the square root of x squared plus h squared equals the r. And so square root of x squared plus h squared, sorry, that's not it. I'm looking for the h, I'm not looking for the r, my bad. So we have the r, which is the, so we're looking for the h. So we're doing r squared minus x squared, and we're taking the square root of that, and that equals to the h, which is this height that we're looking for. And then the minimum LPV is going to be 2 times this is equal to the min LPV. So then we get 2 times the square root of r squared minus x squared. So this is our pair of min and max. And then we're going to do the min divided by the max to get our ratio. And so that's going to be 2 times the square root of r squared minus x squared times 1 over 2r. So we'll take out the the 2. So we're going to end up with square root of r squared minus x squared over r. So that's our ratio in terms of r, because we can define what terms we have and what we don't. So let's just give this a name, right? We're like trying to calculate it, and like we can include this detail later. Like I can find more information about, well, how do you write r in terms of x so that we have this formula just in terms of x? We can do that later, but for now, this is actually totally valid of like, we have it in terms of r and x. That's fine. That's fine. Okay? Like we can do that. We can do that. Okay. And now I have forgotten to label my pieces of paper. So they're very much not in order. That's fine. So look at this. And does this reminds me of something. So no. So we have, there's something I feel kind of related to the rectangle here, because the rectangle we have w over the square root of L squared plus, oh wait, we have a minus here. Oh, no, guys, I did this wrong. Recalculate, my bad. This whole side length is x, but that means that this bottom side, the triangle we're actually looking at, is half of x. So I did this math wrong, so let me redo this. So the max LPD remains 2r, so that was simple enough. But this min LPD, we're actually looking at this triangle right here, where this is the right angle. This is 1/2 x. Damn, I made that mistake earlier today too. of using the entire base instead of half of it. But so this is actually 1/2 x. It's not x. This is r, which is the hypotenuse, and this is h, which is our question mark. So a squared plus b squared equals c squared. So h squared plus 1/2 x squared equals r squared. We want h squared, so we're going to do h squared equals r squared minus 1/2 x squared, which is the same thing as, which is the same thing as, 1/4 times x squared without these parentheses. So we're going to do h equals the square root of r squared minus 1/4 times x squared. So that's what we have. So we're going to place this right here. Oh, times 2. Over here is 2 times this whole equation. So we, in fact, have the minimum, which is 2 times the square root of r squared minus 1/4 x squared divided by 2r, which is our maximum. And so we'll just cross those out. And so our ratio is square root of r squared minus 1/4 x squared over r. That doesn't look like anything, I know, from any of the other shapes. But I feel like if I found another way to write r in terms of x, then maybe this would turn out to look like something else. And now we have a bunch of math papers, a pile of a bunch of math papers, which is so exciting. Yeah, I think that's good on this for right now. Let me know if you have any thoughts. Bye.